So yeah, we're continuing section 5 because we have a couple more examples to do. The first of which we're going to talk about theorem 11, which is the intermediate value theorem for continuous functions. Which says, f is a continuous function on a closed interval AB. Y sub 0 is a value between f of A and f of B. I'll draw a picture about this in a second. If y sub 0 is a point between f A and f of B, that means it corresponds to some value f of C, where the C value, the x value is between A and B. It simply means this. If I have A here and B here, this is f of A. And this is f of B. So if there's a y sub 0 value here between f of B and f of A, then it has to map to some value C that's somewhere between A and B. That's all it's telling us. If you remember from algebra, when we first were introduced to the intermediate value theorem, what did it tell us from algebra? From algebra, what we're looking at here was something like this. If we had some function like this on a closed interval, A, B, if f of A and f of B had different signs, that means there has to be a C somewhere between A and B where f of C is equal to 0. That's when we first introduced the intermediate value theorem back in algebra. But an important concept of this is it's got to be continuous, which means there's no breaks or no jumps anywhere in there or anything that disrupts. It's got to be a continuous function. Because f of C is 0. This concept here, what we learned, that was the consequence for finding a root. Remember what a root was? What is a root? What is it related to? What's another name that's synonymous with the word root? I know you're looking for answers on the sheets. That's what I'm thinking about, making those sheets illegal to have during class. I want to see what you know, not what you can read. You're supposed to do that reading and stuff outside of class. I want to see what you know in this class. The word root is synonymous with solution, x-intercept, factor. All of those mean the same thing. Yeah, you won't see that in your sheets, so don't go popping your head back and forth looking for it in the sheets. So I'm seriously thinking about when you're in class, put those sheets away because You're just gonna break your head doing that. So what this says is when you find a root, in other words, if I give you a function and you factor it out and solve those x's, those are all the roots of the equation. Those are all the x-intercepts, the solutions of them. That's what this is. This is your root. Why is it called a root? Because we know that at x equals c, y is equal to 0. So let's find the polynomial it came from. So x minus c equals 0, and there's your equation. Now, whenever you set y equal to 0, whatever x values that correspond to it are your x-intercepts by definition. So that's what we use the intermediate value theorem for. So let's look at examples. Example 10. Show that there is a root to the equation. Show a root exists for x cubed minus x minus 1 equals 0 between 1 and 2. So how are we going to do it? Using the intermediate value theorem, how do you think we're going to do it? Because remember, what is this doing? This is an equation. It equals y, f of x. It equals 0. Is there an x value that makes this equation equal to 0? Is it asking us to find the x values that equal 0? Or it just that one exists? So we have to look at a couple things. First off, is the function continuous? Is this equation continuous? How do you know?
I think it's a cube root, so
Well, yeah, because basically the root of the cube root equation looks like this. There are no fractions, no radicals, so there's no violations. So x can be negative, positive, and 0. So in other words, the domain of this equation are all real numbers. That's the first thing you have to do. Is it continuous? Yes. Now we have to look at the values at the endpoints. Work those out. So 1 cubed is 1. 1 minus 1 is 0. So we have negative 1 there. 2 cubed is 8 minus 2 minus 1. 8 minus 2 is 6. 6 minus 1 is 5. Since the function is continuous and at the endpoints we have two values with different signs, that means then there exists at least one C inside the domain of 1, 2, where the function equals 0. The intermediate value theorem doesn't tell us how many or where they are. It just tells us if one exists. We couldn't use the intermediate value theorem, but it still could exist, because if they were, let's say they were both negative at 1 and at 2. The graph, remember, it's a cubic function. It could look like that, or it could have something in between there. So it could go like this. So yeah, it just doesn't assure us something at that point. We have to use something else. Let's look at another example. Example 11. Use theorem 11 to prove that this equation, 2x plus 5, is equal to 4 minus x squared, has a solution. Well, in this case, we have two functions. What does a solution mean when you have two functions? Where they intersect. If you only have one equation, the solution is where it crosses the x-axis. If you have two equations or more equations, a solution is where do they intersect, if anywhere. So what's my first step? It has to be set equal to what? 0. So we got to move everything over. Minus 4 plus x squared equals 0. Now what do we do from there? We have two functions. Let's call this one f and this one g. What are their domains? What's the domain of this first one? What's the domain of a radical equation? That's the square root. The smallest it could be is 0. And it goes to infinity. So what would be the smallest value I can use for x to make it equal 0? Yeah, we take the inside, 2x plus 5, set it equal to 0. Negative 5 over 2. Is it puzzle you? So the domain of this one is from negative 5 over 2 to infinity. How about for the other one? For this the 4 minus x squared. What's the domain for this one? Two to infinity, yeah. So what do we notice about those? But even if we did, even when we solve this, we get plus or minus 2. We can say that it goes from -2 to infinity now. But what do we notice about these two domains? What's that? Are they contained in each other? Yes, they're opposite signs. That's true. So it means, are they contained? Is one contained in the other? What does that mean? How's that going to help us? It helps us to look at what domain are we going to deal with. So is there going to be a 0? Will it have a 0? If so, where would it be? Hold it. We have to rethink these. We have to rethink this domain. Because if they're equal, this side has to be greater than or equal to 0. What is this graph? What is the graph of this one going to look like? What's the graph of g of x equals x squared minus 4? We'll move it over here. No calculators. So this is basic stuff. What's the graph of it? What is the basic idea of the graph? What's the square root? No, it's not square root. It's a squared. What does x squared look like? It's a parabola. Does it have a horizontal shift? No. If it had a horizontal shift, it would look like this. Does it have a vertical shift? Yes, since it has this, it's a parabola that goes down 4 spaces. So that's what that one looks like. Now, how's that going to relate to? So how's that going to relate to our function? Yeah, let's graph both of these equations. Let's graph them both. So we have 2x plus 5 is equal to 4 minus x squared. This one looks like what? Is it radical? So we shifted over -5/2, which is -2 1/2. This graph is a parabola opening down, shifting up. And it has intercepts at 2 and -2. So the only place that we're going to have a solution is in the first quadrant, going from 0 to 2. It's got to be between there somewhere. Well, this I haven't plotted it perfectly yet. So what do we do now? The question is looking for prove that the equation has a solution. How can we do that? We know from the graph it's going to have a solution because the domain of this one is there because we cannot have negative answers. And the domain from this one because they both overlap in the first quadrant, that means there has to be an intercept, at least one intercept. Remember, this doesn't find the location of it. This finds us if we have one or not. So our domain from 0 to 2 is contained in the outer entire domain of this. So what if we looked at these two values? What is that going to give us? Plug them into our equation. Remember, we had 2x plus 5 minus 4 plus x squared equals 0. Plug them in there. Sorry. Which one of these are my f? Which one of these are my g? Right, because that's the outer function. So 2 times 0 plus 5. That's f of 0. F of 2, 2 times 2 plus 5. So we have a square root of 5, square root of 9, which is 3. There's a value. We know that the g of x is contained in the f of x, which is the outer function. And it does intersect because of the graph. Zero to 4. So that'll give us -4. Yeah, the whole thing. We have to look at the whole thing at 0. If we take it the whole thing at 0, what do we get? Because this gives us radical 5 at 0. Minus 4 plus 0. X squared is 0. So radical 5 minus 4 is what? Well, yeah, but this has got to be less than 2. So it's negative, let's say it's something less than 2, 1.97. At this one, this part gives us 3. At 2, we have minus 4 plus 4. So those cancel. So that gives us 3. So at there, that's what I was going to. Because the signs are different, there has to be one intersect. Because we have two separate equations, make them into one. So there's, we took F and G, moved them over one, really made this one an H. Look at the domain where the intersection could happen between 0 and 2. Plug them in there. If you have different signs, then they intersect. Yeah, so this is basically what we did. We had F equals G. Then we made it equal to H. Then we found where they overlap, what parts of the domain they overlap. In the first quadrant, in the domain from 0 to 2. So then we went H of 0, H of 2. Only if they have opposite signs will they intersect. If they both come out positive, both negative, that means they won't intersect. Or not in our domain. They won't intersect in our domain, which is from 0 to 2. What about, remember we talked about last time, really quick, before we end the class last time. It's called continuous extension at a point. Or continuity, extension of continuity at a point. This is the example we talked about last time. The function is continuous on the left side as x goes to 0 from the left and as x goes to 0 from the right. It's continuous both sides from 0 to infinity, from negative infinity to 0. So is the function continuous in the whole entire domain? No. Well, the domain was saying real numbers. Or is it continuous everywhere? No, because it has an open circle there. The limit exists. But remember, for it to be continuous, what are the 3 conditions that have to exist? For continuity. For continuity. First one. F of x exists. Or should I say f of c? Because we're looking at limit as x approaches c. It exists, and it's some value. the limit of f of x as x approaches c exists, which means it comes in from both sides. If it exists, it's got to be some value L. Then in order to be continuous, those two have to be the same. The limit point and the value at that point have to be the same. That's what we have to do for continuity. So given any curve, we have a value C. That value must exist. The limit, as we get closer to C, has to exist. This has to be L. So as the functions get closer and closer and closer, they approach the same value. That's how we define continuity. This function, on the other hand, has a hole. So last time we talked about to make it a continuous function, wherever there's the hole, we fix it, we plug it in there. So when x is 0, if we plug in the value of 1, now it's a continuous function. You can do that with these functions. So here's the example for that. Example 12. F of x is equal to x squared plus x minus 6, x squared minus 4, x, we cannot use negative, or you cannot use positive 2. Because it'll give us a 0 on the bottom. From algebra, what do you know about what this graph's going to look like? Does it have any asymptotes? If so, where? Because that's exactly what we're going to cover in the last section, are the asymptotes. Okay, let's first look at what happens. But since we can't use that, what would happen as we approach 2? Remember, for a limit value to exist, it doesn't have to exist at that point. It simply has to approach it. So if we plug in 2 inside here, what do we get? So we have 2 squared plus 2 minus 6, 2 squared minus 4, 4 plus 2 minus 6, 4 minus 4. We get 0 over 0. So what does that tell us? Nope. It has a factor. There's something in common. So what we have to do is rewrite our equations. X squared plus x minus 6. They both have an x. The second sign's a negative, so they're opposite signs. What times what is 6? When you subtract them, you get 1. 3 and 2. And the first sign's a plus, so the bigger number gets the plus. On the bottom, x squared minus 4. X squared minus 2 squared. So it's x plus 2 x minus two. It's a difference of two squares. The x minus twos cancel. There's our whole. Whenever you have, this is called a removable discontinuity. That gives us a whole. At x minus two, or at two, we have a hole in our graph. And now we plug in two, we get 2 plus 3, 2 plus 2. That's our limit value. So can you tell me the location of the hole in our graph? Where? But it's a point. I need an x and y component. No. Everything, it's up on the page. Because where does the function not exist? At what value x? At x equals 2. So that's my x value. The limit point is going to. So that is my hole. That's the location of my hole in my graph. So this graph has one vertical asymptote at -2, and it has a horizontal asymptote at 1. And that's what we're going to cover in the next section.